This problem is going to be very similar to the last problem. If we look at this ramp that they're talking about, or this hill, it's 7 degrees. Here's our car. Our car has got a normal force, and it must have a reactive force. If it doesn't fly off the ramp or sink into the ramp, then they have to be equal to each other. But if it's not going to slide down, then that means the parallel force that pulls it down the ramp must be exactly matched by a frictional force that pulls it up. So we want to know if it's just going to stay on there, what is frictional force if it has to exactly match parallel force? So that would be the minimum coefficient of static friction when force parallel equals force friction. So mu is what we're looking for, and that means force of friction over force normal, but force of friction is force parallel in this case, and force parallel is going to be the weight, let's call that F of G, times sine theta, sine 7, divided by Fg cosine 7, because that's what normal force is. And again, we see the weight cancel out, so this is independent of how much the car weighs, and we see that mu is equal to sine of 7 degrees over cosine of 7 degrees, which is tangent of 7 degrees. And if you calculate the tangent of 7 degrees, you'll find out that it is 0.12. So that's our coefficient of static friction. And it's unitless. This problem is going to be slightly more complicated than the last problems. We have a skier that's 59 kilograms in mass, so we don't have their weight, we just have their mass, starting from rest at the top of a hill, but now they're not going at constant speed and they're not going at no speed. Here they're accelerating, so that's going to make a difference. They start from rest and they get to the bottom in 18 seconds. It's 35 meters away in some time. So that means they've accelerated down the hill. So we can no longer say, like we have been in the last problems, that F net equals 0. That's not true anymore. Now we have to account for the fact that there is acceleration. But we do know that acceleration times mass is going to be equal to F net. So maybe that can help us if we can use this information to find acceleration. Ultimately, the objective is the same. We need mu, which means we're going to have to know force of friction, and we're going to have to know the normal force here. Let's start out here by modeling the hill that the skier is on and the skier. We know that this is a 10-degree hill. I'm not going to draw a skier. I'm just going to draw a point. Simple free-body diagram. We've got a normal force due to the skier's weight. We also have a parallel force due to the skier's weight. There's a reactive force that must perfectly balance this normal force if the skier doesn't fall off the hill, fly off the hill, or sink into the hill. And we have a frictional force. But this time the frictional force is not balanced by the parallel force. Parallel force must be larger. So that means the net force that's on the skier must be equal to the parallel force minus the frictional force. But we also know that the net force is related to the acceleration in this way. Net force is mass times acceleration. So since both of these are equal to net force, we could make an equation here. We could say that force parallel minus force friction is equal to ma. Or we could say force friction is equal to force parallel minus ma. But we also know from our toolbox that force parallel is equal to mg, which is the weight, times sine of our angle, which is 10 degrees. So substituting that, we find that we get force friction is equal to mg times the sine of 10 degrees minus ma. Or we might want to take the m out of there, and we could say that it's m times g sine 10 minus a. Well, that would go in the numerator on mu, because remember, mu is equal to force friction over force normal. We also have a formula from our toolbox for the normal force. The normal force is just mg, the weight, times the cosine of our angle, which is 10 degrees. So force of friction then, so coefficient of friction then, if I substitute the ff and the fn in here, is just m times g sine 10 degrees minus A all over m times g times cosine of 10 degrees. And I have m on top and bottom. I can cancel that out. And that simplifies things a bit. So mu then is just equal to g sine 10 degrees minus A over g cosine 10 degrees. One thing we have left to find, and that's what's A. Well, I know that distance covered during an acceleration is equal to the initial velocity times the change in time plus acceleration over 2 times change in time squared. But this skier started from rest, so that term is 0. So that means d is equal to acceleration over 2 times change in time squared. I know change in time squared. I want to find acceleration, so I'll solve for A. A is equal to 2 times d divided by delta t squared. So I plug in my numbers. It's 2. The slope is 35 meters long. And the time that was required was 18 seconds, and I square that. If I look at what happens to my units, I end up with meters per square second, good acceleration unit. And when I do my calculation, I find out that the acceleration was 0.216 meters per square second. So now I can finally evaluate mu. Looking at this equation here and plugging that in, I now know that it's 9.80 meters per square second times the sine of 10 degrees minus 0.216 meters per square second, all that over 9.80 meters per square second times the cosine of 10 degrees. When I evaluate this, I get the answer 0.154. That's the coefficient of friction between the skier and the slope. This problem is related to the previous problem. It's all the same data, but it says that this new wax the skier is trying will reduce her, it claims to reduce her coefficient of friction by 40%. So it'll be 40% smaller than it is now. And the question is, if this turns out to be true, how long will it take her to glide down the same hill with the new wax? Well, first of all, let's find out what that new coefficient of friction would be if it really was reduced by 40%. And then let's answer the rest of the question, knowing what we know about the time it takes to slide down a slope under a certain acceleration. Well, we learned previously when you're starting from rest, we just used this in the last problem, that distance is equal to a over 2 times delta t squared. Time is what we're trying to find here, delta t. So if we solve for delta t, here's what we get. 2 times d divided by a, the square root of that is going to be delta t. So we know the distance is 35 meters. We just have to find out what's this new acceleration if this wax works the way it's supposed to. Well, what is the new coefficient of friction? Mu new is supposed to be 40% less than the old, mu old. So mu old minus 0.40 times mu old, that's equal to mu new. That'll be 0.60. We'll end up with 60% of mu old, and that was 0.60 times, we calculated 0.154 for our coefficient of friction. So the new coefficient of friction, if this wax works, is 0.0924. How can that help us? Well, we know that F net is equal to m times A, and we need to find A. But F net was also equal to parallel force minus the frictional force, if you recall the free body diagram from the last problem. So that means that acceleration is parallel force minus frictional force divided by mass. Well, let's plug some stuff in there. We know what the parallel force is. It's going to be mg sine of our angle, which is 10 degrees, or slope. But we also know that normal force is related to frictional force. So force friction is mu times force normal. But force normal is mg cosine 10 degrees. So force friction is mu times mg cosine 10 degrees. So that's what we'll put in here for force friction. Mu mg cosine 10 degrees. All of this will be divided by mass. Mass cancels out. Once again, it turns out not to matter what the size of the sphere is. So acceleration here is g times the sine of 10 degrees minus mu times the cosine of 10 degrees. So we can calculate A here. Let's do so by putting numbers in here. G is 9.80 meters per square second. We're multiplying that by sine of 10 degrees, which will be unitless, minus mu, which is supposed to now be 0.0924, times the cosine of 10 degrees. Since we're multiplying meters per square second by things that are all unitless, the new acceleration will also have units of meters per square second. When you do all these calculations, here's what you find out. The new acceleration is 0.810. If you remember from before, that's a larger acceleration than we had with the old wax. So it should slide faster. Now, going back to this equation, the reason that we found this A in the first place, let's plug A in and find our final answer. So delta T is equal to the square root of 2 times 35 meters, all divided by our new acceleration, 0.810 meters per square second. Meters are going to cancel. We'll get units of 1 over second squared, but when we take the square root of that, that's just going to be seconds. Do the calculation, here's what you find, 9.3 seconds. Before it took 18 seconds, so it really is faster.